Hi everybody, good morning. We're going to pick back up where we left off yesterday, so hopefully you got your notes out. Yesterday we were talking about how objects that are in the air on Earth are going to have an acceleration of negative 10 meters per second squared. No matter if they're on their way up, on their way down, at the highest point, anywhere that object is in the air, as long as it doesn't have wings or thrust or a parachute of any kind, it's going to have that same acceleration of negative 10. And we worked through several examples, going back to making some graphs of elephants dropping things. We stopped on this example here where we were throwing a ball upward at 5 meters per second and letting it fall all the way down to the ground 10 meters below. In part A, we solved for how fast the ball is going just before it lands. We found out that it was 15 meters per second going down. Part B, we're going to ask to find the time it takes for the ball to land. So time to land. So we're looking for our time variable, that's our question mark. We know when we land, our displacement is going to be 10 meters below where it started, so negative 10 meters, since it's below where we threw it from. We know since it's in the air, it's in free fall, so its acceleration is negative 10 meters per second squared. And the other information we know that's pertinent here is that our initial velocity is 5 meters per second. We could use the VF as negative 15 as well, so I guess we can list that out. We learned that in part A of this problem. And this really opens the door because we have lots of pieces of information here. We can use them to solve for time. There's several equations you could use. I'm just going to use our delta x equals VF plus VI over 2 times t equation. So plugging in the numbers, negative 10 is the displacement, now velocity is negative 15, initial is 5. So simplifying the parentheses there, negative 15 plus 5 is negative 10, over 2 is negative 5. And so negative 10 divided by negative 5 is 2. So it takes 2 seconds for this ball to land. I'd like to do one more example before we go through the answers to Monday's homework. So we'll just move on to a new example. Hopefully this example helps you out with your homework for tonight. So in our last example, we threw a ball up and let it land on the lower part. For this problem, let's have someone throw a ball upward and have it land at a higher location. So this person's going to throw the ball straight up and have it land up on this higher shelf area. Let's say that our initial velocity is 30 meters per second, so pretty strong throw. And this shelf, we'll say, is 20 meters above your hand that you let go from. And let's find a couple of different things. Let's find the maximum height the ball reaches as part A. And in part B, we'll find how long it takes to land. Now, when we talk about this maximum height, this is going to be a term that we use a bunch going forward. The maximum height, something special takes place. We know it's, as this ball rises, it's slowing down, slowing down, slowing down, slowing down, slowing down. At the highest point, velocity is actually 0. It's not going up, it's not going down. It's turning around. And then after that highest point, it's speeding up on the way down. Speeding up, speeding up, speeding up. So if we're talking part A here, finding the maximum height, we can pretty much stop the problem right at that highest point. We don't need to worry about anything that happens afterwards. Which means, if our initial velocity we threw it at is 30 meters per second, the final velocity at the top is 0. Okay, for a maximum height problem, you're going to want to use a final velocity at the highest point of 0. Continuing on, since our ball is in the air on Earth, we can assume its acceleration is -10. And finally, if we want the maximum height, the variable we're looking for is delta x. So solving for or looking for an equation that doesn't have time, we've got vf squared equals vi squared plus 2a delta x. So 0 squared equals 30 squared plus 2 times -10 times 20, or times, sorry, not 20, times delta x. We're looking for that maximum height. So 0 equals 900 minus 20 times delta x. Move the 900 over, divide by -20, and our maximum height is 45 meters. Now that 45 meters is above where the hand was. So it's 45 meters above where this ball started in the person's hand. So if I label it along the side up here in the diagram, this is 45, not bad. This is 45 meters. Part B to this same question, we can start it over here. I want to know the time it takes to land. So we're looking for time. We know the acceleration in the air is -10. We know the initial velocity is 30. And we know by the time it lands, its displacement is 20 meters above where it started. So I'm going to use a positive 20, whereas in the previous example, the ball landed below where it started, so we had a negative displacement. Here we have a positive displacement. So giving ourselves some space here, we're going to use the delta x equals vit plus half at squared equation. So we can plug in our information. We know 20 is our displacement. Initial velocity is 30 times time plus half, -10 times time squared. At this point, you should be looking at it and saying, uh-oh, we've got a time and a time squared in the same equation. This is shaping up to need the quadratic. So we get everything on the same side of the equal sign. And I'm going to put my t squared term first. So half times -10 is -5 times t squared plus 30t minus 20. So -5 is A, 30 is B, -20 is C. So our time is going to be equal to b squared, negative b plus or minus the square root of b squared minus 4ac all over 2a. Simplifying here, we've got time equals -30 plus or minus the square root of 30 squared minus 4 times -5 times -20 all over 2 times -5. So simplifying again, -30 plus or minus the square root of 500 all over -10. This is going to give you two answers, one when you add, one when you subtract. When we add, actually I don't know whether we add or subtract, I just got two answers. I got 0.76 seconds and 5.2 seconds. So we get two positive answers. Normally we can rule one of them out for having a negative time not being an option. Here we have two answers and we have to choose which one represents the time when this ball lands. So you have to think about what's happening in the problem. The ball starts out at a certain height, goes up 45 meters, and then lands. What we just solved for mathematically is the time it takes to get to this height of 20 meters up. Well, our ball is at that height twice. Once on the way up, and once on the way down. So that's why we have two positive times. Our on the way up time is here. And when it lands, it's here. So to answer our question for part B, when does this ball land? After 5.2 seconds. Now last but not least, let's go over the answers to the first part of worksheet 5 real quickly. Number 1 says, what does it mean for an object to be in free fall? We talked about this yesterday. An object's in the air on Earth and it doesn't have wings, parachute, thrust, or contact with the ground. Number 2, what is free fall acceleration on Earth? We're going to approximate it to be negative 10 meters per second squared. Number 3, we're matching up which graphs represent free fall velocity and displacement of an object which is thrown upward and later caught at its original height. That's going to be choice B. Question B, which graphs represent the free fall displacement and velocity of an object which is dropped from rest? So if we're dropping it from rest, that's picture E. Last but not least, same kind of deal. We got pictures to match. Which graphs show the free fall velocity and acceleration of an object that's thrown up and later caught? That's going to be picture D. We throw it up, slowing down, slowing down, slowing down, turns around, speeds up in the negative direction, and the acceleration the whole time is negative 10. And letter B, which pair of graphs shows the free fall velocity and acceleration of an object which is dropped from rest? That's going to be picture F. We made that graph yesterday. Speeds up in the negative direction, and again, your acceleration is negative 10. Hopefully this is a good enough introduction to get you to finish the backside of worksheet 5 as homework, numbers 5 through 10. Should be getting whole number answers. Make sure you show all your work, show which equation you used, and be careful with your algebra, and label all of your answers. Good luck. See you on Wednesday.